Hello and welcome to another video. In the last video, we have seen about proportional and proportional integral controllers. Now we will discuss about proportional derivative and proportional integral derivative type of controllers. Like in proportional integral controller, here we have the proportional component Kc into error and the derivative component Kc into tau d into d derivative of error d epsilon by dt. Now this is the error. The output of the proportional derivative controller will be P, and the P will be Kc into epsilon plus Kc into tau d d epsilon by dt. Now what is the significance of adding this component? So the proportional as well as the derivative component. Suppose you have some error which is changing like this. So the error is a into t, and the error is changing like this. So until this point it is constant, and then it is at. So what happens to the controller? This is the controller output. On the top we can see the controller output. So until this it is some constant value. After that, this part, the step change part, is the derivative action. So this is the derivative component. So for a constant slope, we have a constant. The derivative of a ramp is a step. And this linear part is the proportional component. So combining this both, we have this. Combining this both, we have this, the output of the controller. Now here we have two adjustable parameters. One is the gain Kc, another is the derivative time tau d. So these two parameters we can adjust to take suitable proportional derivative controller. This controller is also called a rate controller due to the influence of the derivative part, or anticipatory control. It is taking the rate of change of error. So that is why it is called an anticipatory control. So we are taking the slope of the error to decide what is the control action required to eliminate that error. So this is also called as anticipatory control. Suppose our error is at, it's curve like this, a ramp input. Then the output of the proportional derivative controller will be A into KCT plus A into KC tau d. So after this derivative part, we will get the proportional derivative action to be this. The controller takes action to counter the anticipatory change in the error that is predicted from the slope of the error versus time curve. So there is a prediction from the slope of the error. So that prediction is used by the controller to take control action. So anticipatory, it is anticipating some change in the error. So the slope will give an information that in future the error is going to increase or decrease. So based on that, current control action is taken. So that is why it is called anticipatory control. And the transfer function of the controller is Kc into 1 plus tau ds. Now we will see what a proportional integral derivative controller does. So here we are using a PID controller. The error is the to PID controller, and there is a control action P. So this control action P is nothing but it has a proportional part Kc into epsilon. It has a derivative part Kc tau d d epsilon by dt. It has an integral part Kc by tau I, integral of 0 to t epsilon dt. So we are integrating the error, we are taking derivative of that error. Also we are taking the proportional value of that error. So it is a combination of proportional, integral and derivative modes of operation. Here the transfer function is derived like this, Kc into 1 plus, looks like this, Kc into 1 plus tau ds plus 1 by tau is. Now it has advantages of both the proportional, integral, and derivative modes. Now we will see few nodes which will be helpful in deciding what controller is to be chosen in which city. Suppose you have some noisy error signal. Then if we are using a derivative control, we are taking the derivative with respect to the error. So if the error is some noisy signal like this, then the derivative action is based on how rapidly the error is changing, how fast the error is changing, not the magnitude of the error. So it doesn't care about the magnitude of the error, it cares about the rate of change of error, how fastly the error changes. It also doesn't care how long the error is persisting. Like how in the integral controller, we take care of how long the error is persisting. If the error is persisting for a long time, then we take integral part will add up and integral action will be more and more into the plant. But here in the derivative part, the how long the error is persisting, so they not taken into consideration. The only thing that it takes into consideration is the how rapidly the error is changing. So it is based on the slope of the error at that particular time instant. Therefore, the noisy error signal or the rapidly changing error signal will cause large derivative response. So if there is some noisy error signal, it will cause large response. In such situations, we need to avoid the derivative control. So if the error is very noisy, we need to avoid this derivative control. The selection among different control systems depends on the particular application. If an offset is tolerable, if it is okay to have some offset, say if you are giving a step input and the controller takes some action and it is okay that you settle at some other different value with a small offset. So this difference or the deviation from the reference or the set point is offset. So whenever you use a proportional controller or a proportional derivative controller, you often end up with offset. So if it is okay that if an offset is tolerable, then we can use a proportional controller. And if no offset is tolerable, if offset is avoided at any cost, then we go to the proportional integral controller or proportional integral derivative controller. So this integral action will help us eliminate that offset. But this integral action has a drawback that it results in oscillation. So this integral controller will result in oscillation of the response. So if excessive oscillations needs to be eliminated, then derivative action might be added. And the drawback of derivative action, which we have seen earlier, that for a noisy error signal, we need to avoid the derivative control. So this is a combination. The choice of controller, depending upon it, upon many factors. It depends upon the process. It depends upon the error. It depends upon the user's requirement, whether an offset can be tolerated, whether there should not be any offset. So there are many factors which will determine which controller we can choose. We will see more examples to bring out the advantages and disadvantages of each modes in next videos. Thank you.